Welcome everyone, and thanks for watching. So this is our 20th live stream geometry. So we have 3 people here with us right now. And today I'm going to do problems from the International Festival of Young Mathematicians in Bulgaria. So I don't know a huge amount about the contest. I saw the Facebook page, but it seems to have some really nice problems. I was really impressed with how elegant a lot of the problems seem to be. So with that, let's get started. So I'm going to share my screen. Hold on just a second. Let me find it. It should be this one. All right. You guys all see it? So here's the first one.
Oh, yes.
All right. 2019. So we have the incircle of a triangle ABC. And it's tangent to AB and AC at K and L. All right, so I'm going to draw that. The altitude AH, we draw the altitude AH, and we see where it intersects the perpendicular bisector, I'm sorry, the angle bisectors of ABC and ACB. Okay, so let me draw in K and L. So should be K. First, I'm just going to draw all the points and then I'll name them. So this is K. This is L. This is P. And that's Q. And the altitude's AH. So that point is H. Let's make it a little bit farther from the circle itself. And we want to show the midpoint of AH lies on the radical axis of 2 of the circles. All right, so I'm going to delete some stuff here. Obviously, these 2, here's the end center, so I'll call it I. So it lies on the 2 angle bisectors. All right, so I will hide, and I'll hide that. All right. All right. So the midpoint of AH. So let's see. Okay, so we draw KPB and LQC. So here's KPB, LQC. And, oh, it looks like these circles intersect on BC. Is that true? Yeah. Is that obvious? Let's see. It's probably just an angle chase, I would guess. Because if this circle intersects at X, then we have angle PXC is equal to angle PAB. So basically we want to show P, I think it's the same as showing AKLP is cyclic. Actually, I'm not sure. Well, let's just assume for now they meet on BC. I'd guess that's probably an angle chase. So, I mean, basically, we want to show D has the same power with respect to both those circles. It's kind of interesting. Yeah, I'm just trying to think in my head. If we can prove that these circles meet on BC, right? It shouldn't be that hard. So angle PEC is equal to angle PKA. I'm sorry, is equal to angle PKB. Or like if I hide this circle, angle PEC is equal to angle PAB. So angle P, I'm gonna unhide it. Let me call the midpoint M instead of B. I wonder if I can use Casey's theorem. I mean, basically, if we draw this point, we want to show M, D, and E are collinear, right? Oops. We want to show M has the same power with respect to both those circles. Here it almost looks like it's MP is tangent, but yeah, that's just a coincidence. So yeah, maybe we could show M has the same power with respect to both of them. That would prove it. This is tricky. Let me draw the centers of those circles. So AKIL is cyclic, right? Oh, it looks like that passes through D. Is that true just by Mikkel's theory? Yeah, that's just Mikkel, right? So once we know E, once we know these two circles meet on BC, then that would just be Mikkel's theorem. I wonder. Let's see. So JF and G are the midpoints of those, I'm sorry, the centers of those three circles.
Midpoint of altitude is related to in center by a configuration, if I remember, that MI and the external point of X circle and MD and the X center are collinear. The D means foot of perpendicular from I to BC.
Okay, so
it's a well-known result that M, N, and AX center
are collinear.
And MI and contact point of X circle at BC are collinear.
Yeah, that's the IM lemma. So, oh, it looks like it passes. No, that must be a coincidence, right? That IM passes through G. Yeah. Okay. Yeah. So, yeah, I mean, so, yeah, if IM, so, yeah, we would have like OC is equal to BN, right?
Yeah.
And then you're also saying
Mn passes AX center.
Mn passes through the AX center. Okay, so
one final thing that midpoint of altitude remains is the 9-point circle. No,
oh,
but
yeah.
that's the midpoint of AX now. So,
I'm just going to keep that in mind for now.
yeah.
But that's a good point. I feel like DIQP might be cyclic, actually. This reminds me of another problem. Let's see. Yes. Yeah. I think that's like Mikkel's used a different way. So I don't know how there's this other problem on my channel that I did, though, where I think you can also show DIPQ as cyclic by Mikkel's theorem. Okay, so I don't know if that really helps. It might, though. Okay, so we have the circumcircle of BKP. Let's see something.
Is MI parallel to AC?
I doubt it, because by symmetry, then it would also be parallel to AB, I would think. But yeah, no.
Oh.
It's all right then. I'm trying to use Casey's theorem. Let's see. Oh, I think MI is equal to, or ME is equal to MN, it looks like. Okay, that will probably help us. So ME is equal to MN. I'm not sure right now why that's true, but that might help. So basically, we want to show angle MNB is equal to angle DEN, if that's true. And DEN is DKB. So we want to show DKB is equal to MNB. Huh. It's interesting. So MN and the X center are collinear, you said, right?
Yes.
I wonder if that helps us. Yeah, first of all, can we see why HN is equal to HE? Well, that's the same as saying that H has the same power with respect to the in-circle and, wait, so HE, yeah, I feel like there should be a way to prove that. So first I want to show HE is equal to HN. So we have HE times HB is That's the power with respect to this circle. And hn squared is the power with respect to the n circle. And he times hc is the power with respect to that circle. Let's see something. I'm like trying to use the power ratio on that. Let's see. I wonder if yeah, it's so hard to see, but I think this circle through D, H, and E passes through the intersection of AH with maybe that's obvious actually, because want to see what I mean? Yeah. Is P the circumcenter of KEN? That would be interesting. Yes, it looks like it. Very nice observation. Let's see if we can prove that. And then, so we want to show P is the circumcenter of KEN. And I think, yeah, because P lies on the angle bisector. I forgot to use that. But yeah, since P is on the angle bisector of KBE, that means PK is equal to PE. So if we can show AH as the perpendicular bisector of EN, that would prove it. So let's see. So P would be the circumcenter of KEN, and Q would be the circumcenter of LEN. Feels like the problem has to fall apart once we know all this. Let's see. So I wonder if KELN and AH concur. No, I don't think so.
I think we can try defining N to be the reflection of E and then prove that IMB is 90 degrees, or maybe IM parallel to PH.
IN is parallel to EH?
Now, I mean, we can assume that HE is equal to HN and then try to prove that IM is parallel to AH.
Okay, so we're assuming EH is equal to HN, and then we're trying to prove that IN is parallel to AH. Is that what you said?
Yes.
Well, we know IN is parallel to AH because IN is perpendicular to BC and AH is perpendicular to BC, right?
Yeah.
So yeah, we have angle, assuming that HE is equal to HN, we have angle DEN is equal to angle DKN. We want to show that's angle D. We're going to show that's MNE. Yeah, how do we use that M as the midpoint? So yeah, I know you gave a couple different ways to use it, Anmol. I'm seeing, let's see.
We can maybe use that MJ is parallel to IH or some form of midpoint theorem. Because J is the midpoint of AI.
Okay. Yeah. Yeah. Okay. Yeah. MJ is parallel to IH.
Is J also on the radical axis, or it just seems like that?
I don't think so. No.
Yeah.
Hey, Rodrigo. Thanks for joining. So yeah, this is a little bit of a tricky problem here. We want to show that M lies on the radical axis of those two circles. So yeah, I'm guessing the easiest way is probably to show it has the same power with respect to them, right? So how would we show that? Let's see. I kind of like using Casey's theorem. I just don't have an exact idea of how to do it. Let me try one more thing here. What can we say about MF? Let's see. Let me try something. Is I? No, I don't think that's true. I'm gonna ask if IH is perpendicular to FG, but I don't think it is. No. I like using that MJ is parallel to IH. Also, IM bisects AN. No, I'm sorry, IM doesn't bisect AN. Yeah, so what if we label like the midpoint of AB? Then MO is parallel to BH. Then we would have JO is parallel to BI. Yeah, I'm trying to figure out how I use the final condition. So do I use the radical axis theorem? Like, how do I calculate the power of M with respect to those two circles? Yeah, I like the fact that P is the circumcenter. I feel like that has to be useful somehow, right? I would be very surprised if that wasn't useful, that P is the circumcenter of KEN. Let's see. Is there any way to calculate angle MNB? Let me think. Angle MNB. I feel like that's key. So MN passes through the X center. Let's see. Yeah, what if we reflect H? Let's do this. Let AI Can't do much. I want to show angle MNB is equal to angle DEN. I feel like that would help us. But MNB, that's tricky to compute. Let's see. draw on this other circle just for. I wonder if there's like another circle that passes through E and N.
I think we can extend DE to meet circumcircle KIDL at some point.
Okay.
According to my diagram, that point turns out to be reflection of A. I mean, if that point is X, then AXHN is a rectangle.
Ah, okay.
And AO is also parallel to BC.
Let's think about this. Yeah, because J is the center of the circle. Let's see. So, yeah, we're letting ED, I'll just call it O for now. Yeah, okay, so it's kind of like this, right? So, all right, I think we're getting somewhere here. So basically, we want to extend IN to meet this circle at a point O. And then we want to show O, D, and E are collinear. So we want to show O lies on the radical axis of those two circles.
Yeah, because we know that AOHN is a rectangle. So AOEH should be a parallelogram. I'm assuming that EH equal to EN. And so M should also lie on OE. We can then safely eliminate the midpoint of AH.
So yeah,
I think we should prove that H equal to HN because the angle change from here seems like doable.
yeah. I mean, is it clear that, like, did you say, you can show that like AOHE? Okay, so basically, I'm going to hide J for now and a couple things, but like if we draw this picture, is it obvious that AO is parallel to BC? Okay, so we draw the circumcircle of AKDIL, right? Because
Yeah, I have defined O to be such a point. I do not assume that O, D, and E are collinear.
okay, so
Yeah, I have assumed that O is a point such that AO is parallel to BC.
okay, so you define O to be the parallel to BC, and then
Yes. Then I observe that AOHN is a rectangle.
oh, because angle AOI is 90 degrees. Okay, so
Yeah. And since that is a rectangle, so AO equals HN. And I am assuming that HN is equal to HE. We will prove that later. And if HN is equal to HE, then AO is equal to HE, which means that AOHE is a parallelogram.
okay, all right.
And
So
midpoint of AH and midpoint of OE are basically the same.
I like it. That's a good idea. Okay. So we want to show HE equals HN. and that would solve the problem.
Yeah, I think we can define E from N or N from E and then so that QLCE is cyclic.
So we actually don't, we still haven't proven yet that these circles meet on BC, right? Like we haven't shown yet that E, like you see what I mean? Like we originally assumed that BKP and LQC concur on BC. But we still have to prove that, right?
If we assume E to be reflection of N over AH and then prove that QLCE is cyclic, this would imply both of.
So basically, yeah, let E prime be the reflection of N over H.
Yeah.
So if we sort of let, I'm just going to call it E prime for now. If we let E prime be the reflection of N over H. Whoops. We want to show DE E prime KP is cyclic.
Here, because we know that Bn equal to Bk and BP common and both the angles same, so triangle BPN congruent to triangle BKP. I think we should try proving that for the other side. That seems much clearer.
Okay, so basically, yeah, because then we have PE prime equals PN is equal to PK. And so then we know, yeah, from there we could show, since BP is an angle bisector, that BKPE is cyclic. But maybe we don't even need it to do with it, because here we know that, well, yeah, I kind of like that. So, yeah, I like defining E prime like that. And then we could show, yeah, because then Pn is equal to Pe prime is equal to Pk. Yeah, let me keep it in the circle. So yeah, that solves the problem. All right, so I'm going to start writing.
Because okay, I did the angle chase and I got that PKA is equal to PNC by congruence and PNC is equal to E prime B and hence PK BE prime is cyclic.
I think I thought about it a different way. That's probably the same thing. Oh, because you're just saying that, yeah, this angle is equal to this angle is equal to that angle. That's even easier. Okay. Yeah, I like it. Okay. I will start right up. So, all right. So let me, and yeah, do we need point D? I don't even know if we need it. But I'm just going to leave it there for now. So, all right.
I guess we don't need the circle IPQD for now.
Yeah, we don't need that circle. I agree. Okay. Whoops.
Yeah, but we will need D later because we would like to prove that ODE prime is collinear.
Okay. I'm going to hide it for now, but I'm going to bring it back later. So, yeah, I'm going to start. So I haven't done this before, but I'm going to type up the LaTeX in words so it doesn't overlap the diagram. Let me see how this works for you guys. So, Well, actually, no, it's going to be a little hard. Okay, so I'm just going to do it the way I usually do it. So let IN meet the circle AKIL at point, let the parallel through A to BC meet the circle AKIL at point O. Okay. And then angle AOI is equal to angle ALI is equal to 90. So that means OI and N are collinear. Now we can define E prime. Okay. Let me delete point F. So let E prime be the reflection of N over H. Then we have angle PE prime N is equal to angle PN E prime, which is equal to angle PK B, which means that PE prime BK is cyclic. All right. And similarly, we could draw that circle. And then similarly, PE prime CL is cyclic. And so that means that E prime equals E. Whoops, PE prime, wait, what am I doing? Oh, QE prime CL is cyclic. Okay. And so that means that E prime equals E. And then, so we could just call this E for now. I'll just leave it as. Okay. And then by Meckel's theorem, the three circles concur at a point D. PKBE and QLCE concur at a point B. All right. So I'm gonna draw D. Whoops. And then I forgot. So basically OE, we want to show OD and E are collinear. And then it'll be clear, it's clear that that bisects AH. So how do we show OD and E are collinear? probably an angle chase, right? So we want to show angle ODI plus angle IDE is 180. I think, do we want to show angle ODI is equal to angle BKD, which is equal to angle ALD? So we want to show angle ODI is equal to angle ALD, is that right? I feel like it should just be an angle chase that OD and E are collinear. Let me just think this through. Let's see. Maybe I could show, I'll try to show angle ODK plus EDK is 180. I think that might be better. So ODK, it's 180 minus OAK, which is angle KBE.
I think this is a simple angle chase that angle ADL, no, angle ODL is equal to angle OAL is equal to angle LCB, and because DLCE are cyclic, this implies ODE collinear.
Say that one more time. So angle ODN.
No, ODL.
Angle ODL.
Yeah. ODL is equal to OAL is equal to OCB, which is 180 minus EDL.
Okay, so angle ODL is equal to angle OAL is equal to angle ACB is equal to angle
equals 180 minus EDL.
Okay.
This implies that ODE are cyclic and hence ODE are collinear and hence we are collinear.
Okay, so that means that OD and E are collinear. All right, and then from there we can finish it off because since HE is equal to HN is equal to AO, that means OE bisects AH. I'll just say that. I think it's obvious from there. All right. Oops. All right, thanks for the idea. That's a really cool solution. me just draw an M just for the heck of it. And I will move on to the next problem. That was a cool one. All right. Let's see who's all right, we still have Rodrigo on. So we have an isosceles triangle with circumcircle omega, right? So ABC. So I'm going to draw the circumcircle. And O is the center. Okay. H is the foot of the altitude from C to AB. Oh, they didn't say. Actually, I'm assuming it should be C is this top point. But yeah, they don't say what if CA is equal to. But yeah, I think C should be the vertex. So H is the foot of the altitude from C to AB. All right, I'm going to cheat here. Call that H. All right. Oh, no, it should have been, because otherwise H and M are the same point. So I think actually it is like this. Okay. So okay, that's interesting. So M is the midpoint of AB. And H is the perpendicular from C to AB. X is so the circle with diameter CM is the circumcircle of CHM, right? So they're saying this point is X. XH intersects the circle again at Y. CO intersects AB at D. Interesting. And we want to show that this circumcircle of YHD is tangent to omega. All right, interesting. So I'm going to hide some stuff here. Hide. CO and D, we're going to want to draw that. So are those lines parallel? Let's see. They almost look parallel, but I don't think they are. No, because like here you can see they're not parallel. Okay. All right, so whenever I see tangent circles like this, I kind of think homothenty, right? So it's like we want to draw YD, and then we want to show if it meets this circle at a point E, we want to show EX is parallel to HD. All right. So yeah, let me hide this circle for now. If we could show EX is parallel to AB, that would solve the problem. Feels like Rhimes theorem, doesn't it? Or Rain's theorem, I don't know how to pronounce it. So how do we show those are parallel? It feels like an easy problem, but let's see. We have to use that M as the midpoint of AB. So maybe that'll make it a little trickier. So I think it's the same as showing arc BX is the same as is equal to arc AE. So I think so yeah, there's a bunch of different equal angles that it's equivalent to. So we want to show AYD is equal to BYX. AYD and BYX. Can we show those are the same? So yeah, we want to show YX and YE are isogonal with respect to angle AYB. Let's draw that in. .7, 27.7. Can we use the isogonal line lemma? Isogonal line lemma might be a little tricky here. Let's see. BYH equals AYD. That's the key here. So yeah, I forgot to draw. So H, we have to keep in mind H is the foot of the altitude from C to AB. So is that the 9? No, that's not the 9-point circle. That's interesting. We have a circle passing through H and M. Let's see what the center of that circle is. Oops. Not that circle. Center, I think circle E. So yeah, do we have similar triangles? AYD. Is BYH similar to AYE? Whoops. I wouldn't be surprised. 119.7. Yeah, basically we want to show BYH is similar to AYE. And we know they share one angle. Is it just a spiral similarity? BYH and AYE. That's the same as saying YHA is similar to YBE. Same thing. We know angle CXN. Yeah, I wonder if it's, let's see. Yeah, it seems like there just has to be yeah, BYH we want to show similar to EYA. Trying to see something. I think BY is B the circumcenter of YMX? No, that was just that picture. Okay, so we want to use that MXC. Yeah, let's add in another point here. So these points meet on the circle. That might help. Whoops. Okay. Is GY equal to GA? No. Just looked like it. It's a Pascal's theorem. So BYH is also just BCX. That seems like it might be easier to compute. So angle BCX. Or I wonder if BCX and AEC, they don't look similar. Yeah, it's weird. Yeah, it's hard to use the fact that CO intersects AB at D. So yeah, we want to show another way is to say AYD is equal to BCX. And we know that CXM is 90 degrees. I wonder if it would help to draw this point here. So MI is perpendicular to CG. I don't know if that would help. Yeah, it feels kind of like Pascal's theorem. So I feel like there's so many theorems about isogonality that it has to have a way of doing it. Let's see. I'm just going to try to use the isogonal line lemma. Oh, A, F, and X are collinear. That's interesting. Why is that true? Oh, no, it's not true. Someone joined with the name. Sorry. Hey, thanks for joining, Math. So what user are you on Discord? So we're currently on our second problem here. So yeah, if you want, you can talk out loud, or you could just type in the chat if you feel better about that. But yeah, thanks for joining us. All right. Hello. All right. So what was I saying about isogonality? Oh yeah, if AX meets BE at a point, is that point like, I wonder if that point lies on the angle bisector of XYE. No. Okay, scratch that. This is a tricky one. Let's see. Trying to use ratios in my mind. So we have like a spiral similarity, right? Is YDA also similar to YXB? Let's see. I think they are. Yeah. So we have like two similar. So YDA is similar to YXB, and YBH is similar to YEA. It almost seems like the problem has to be solved from there. You think AE is equal to BX? Yeah, if we can show AE is equal to BX, that would solve the problem. Because, yeah, we want to show AB is parallel to EX. And yeah, that's the same as showing AE is equal to BX. All right. What was I saying? Yeah, we have like two spiral similarities. So really we could show either one. So we want to show YDB is similar to YAX. Yeah, there's so many different equivalent things we could prove. I wonder if we could use Pascal's theorem somehow. I just don't know on what. What's a good way to use Pascal's theorem? Or maybe projective geometry. I haven't used that AB is equal to AC. Yeah, this feels like it has to collapse, this problem. I just don't know the trick. We just have too many spiral similarities, right? I think EDB might also be similar to YBX. Yeah. Triangle EDB is similar to YBX. Is there any way we can show that?
Isn't CY the median of the triangle ABC?
Is CY the median? It might be. I think so. I don't know why. I've gotten so bad with medians lately, but it's an important idea. So yeah, CY is the median. How do we prove that? So yeah, do we have any harmonic? Let's see. Let me draw the tangents. So I guess the tangent to the circle at A is parallel to BC, so that's pretty useful. And those three concur. So that's the thing. So we're saying AYBC is a harmonic quadrilateral. Is that obvious? Feels like it has to be provable. AYBC we want to show is harmonic. Is there something we can project through? Can we project through G? But where would B go to?
Also, is B the midpoint of arc YX?
I don't think so, because I think yeah, no, it just looked like it in that figure, but not necessarily. But I mean, yeah, so we want to show AYBC is harmonic. That feels like it has to be provable. I think you just have to project through the right thing. So let's see, AYBC. I mean, that's the same as saying if we draw this, like if we project through X onto the line AB, then that's the same as saying that we call this point down here F. We want to show A, H, B, and F are in harmonic conjugation. Let's see. How can we show it? How can we show that? We could project through X. Let's see. I keep forgetting how we define X, but
By the way, I think proving that CY median solves this, because it's a well-known fact that CDH is tangent to the circumcircle ABC, and if we produce the tangents at C and Y, by definition of median, we know that they would intersect at AB and let that point be T. Then by power of point, we claim that Ty square equal to Th times HD, which would conclude the problem.
all right, let me write that up.
Ty is median.
So you said, first of all, you said CDH is tangent. Okay.
To AB, that's just an angle change.
Okay. So yeah, I'm gonna write that up. All right. Hold on just a second. All right, so what did I add to the figure? Let me delete G. All right, so everything else I think was already in the problem. So, first I'll write it like this. So, since angle CHD equals 90, that means the circumcenter triangle CHD lies on CD. And that means that, or I'll say lies on OC. And that implies that the circumcircle of CHD is tangent to the circumcircle of ABC. That's kind of how I thought about what you just said. All right. Oops. Okay, so I'm going to draw that circumcircle. And so that means a homosity at C takes one of those circles to the other. And so did you say, what was your next step?
I said that construct tangents to the circumcircle of ABC at C and Y.
At C and Y, okay.
Yeah, by definition of median, we know that they would concur somewhere on AB. Yeah, we are assuming here that CY is a median. We have to get to prove it. I think that would be something related to harmonic conjugates.
So you're saying, yeah, you want to prove that the tangents at y and c concur with AB, right?
Yeah. If we name that concurring point T, then we claim that Ty square equal to Tc square, which is Th times Td. This
Okay.
is like, yeah, Ty square equals Tc square equals Th times Td.
dH times BD.
Yeah, because CHD is tangent at C.
Okay. So yeah, I think I see what you're saying. So yeah, so we want to show AYBC is harmonic, basically. Is that obvious that AYBC is harmonic? Hmm. Yeah, I'm trying to figure out how to show AYBC is a harmonic quadrilateral. It feels like it should be easy, but I'm just not sure how to do it. Yeah, what do we project? X seems like the natural choice. So, I mean, we want to show XB, XH, XC, and XA is harmonic. Is there something else we can project onto? So, maybe put this over here. I'm not sure. Oops. Yeah, let me move this over a little bit. All right. I'm a little confused here. ABYC, we want to show that's harmonic. I'm going to draw that tangent line again. Yeah, there's a lot of things I'm thinking of. I just don't see the. Yeah, it seems like projecting through X is like the most natural thing. So yeah, if we let CX meet AB at a point, I feel like there has to be a way to show that those are in harmonic conjugation. So if we let CX meet AB at, this is getting in the way. I'm just going to minimize that for now. So if we let CX meet AB at a point F, can we show that A, H, B, and F are in harmonic conjugation? So X, yeah, how would we show that? A, H, B, and F are in harmonic conjugation. Is there some kind of right angle we can use? Let's see. So, well, actually, this might help. So basically, M is the, I should have drawn the midpoint of BC, really. So M is the circumcenter of ABG. So yeah, there's a lot more. Okay. Now I feel like I'm getting somewhere. So these concur, it looks like. This is the orthocenter of ABC. And so we want to show G, what did I want to show? AHBF are in harmonic conjugation. So we want to show GB bisects angle HGF. Which looks true. Yeah, there's too much structure here. The problem feels like it has to collapse. So, and there's this point. Yeah, because, so what did I say? A, H, B, and F. Yeah, so let I be the orthocenter of ABC. We would want to show that G, J, A, B, and CX are concurrent. Yeah, there's just too much going on here for it not to be solvable. So yeah, so IGXCJ is cyclic. Yeah, these concur at point F. Okay, yeah, so I can show it's a harmonic quadrilateral. I can show AYBC is a harmonic quadrilateral. So All right, let's see. Hold on just a second. I think we're close here. I don't want to give up on this problem. Okay, so once I showed A, Y, B, C is harmonic, then you were saying draw the tangents at Y and C, right? That's what you were saying, right?
Yeah.
And they meet on AB. And then we use power of a point a bunch of times. So
Yeah.
so then that would show that this angle, let's see. Do you know what you would do after that? I think you said that would solve it, right? It's a median. So, YC. Yeah, CY is like once we know I guess once we know ACBY is harmonic, then that means CY is a symmedian, right? Yeah. So so I see that CY is a symmedian. That makes sense to me. How do we use that to then finish the problem? Once we know that CY is a symmedian.
I think we should mark the orthocenter in the problem.
So this is
I is the orthocenter.
Yeah. So yeah, I've shown that this is a harmonic quadrilateral, A, Y, B, C. I think you had an idea to finish off the problem once I knew that, right? Or didn't you have an idea on how to finish the problem once I got that?
Yeah, I had the idea that TC square equals TY square, and TC square is TH times TD. And this
Okay.
implies that YHD is tangent to TY.
That YHD is tangent. Oh, because okay. So hold on one sec. All right. So I think I got this. I don't even know if we need this step, but basically, okay. So let me write this out. Yeah. Let me call this J instead of I. So I'll say all right. So let's do this. I'll draw the midpoint here. So let J be the ortho center of triangle ABC. . Then we have angle JGC is equal to angle JXC is equal to angle JFC is equal to 90. And so that means that JGXCF is cyclic. All right. And then we also have BGFA is cyclic. So BGFA is cyclic. I don't even know if we need that actually. I'm just going to write it out just in case. I'll say cyclic with circumcenter M. Okay. And then I think that might be important. Yeah. So once we know that, I don't even know if we need point E in the problem. So let FG meet AB at a point. So, or I think that's what it was. Angle chase. So, so by the radical axis theorem, FG, CX, and AB are concurrent. BXY is equal to MCA. But write out some more steps. I don't see exactly how you're doing it. Write out some of write out the full angle chase. All right. BXY is equal to BXA minus 90 minus HCM. Okay. Angle BXY is equal to angle BXA minus BX. What's BXY is BXC minus 90.
Here what he's saying that BXY is BXC minus HXM minus CXM, and CXM is 90 and HXM is HCM by cyclic quadrature.
HXM is HCM. Okay, so he's proving that that is a semi. Okay, so I think I had a different idea in mind, but okay, I think his way shorter. So, so he's saying angle BX. Let me write it. All right. So BXC or BXY is BXC minus HXM minus angle MXC, which is equal to BXC minus HCM minus 90. And that's 180 minus angle BAC minus angle HCM minus 90. I'm just going to write it 90 minus that. Okay. And 90 minus angle BAC is angle ACH. Which is equal to angle ACM. Okay. So that means that CY is a symmedian. Okay. And that means that ACBY is harmonic. And once we know that, that looks weird. Oh, because I put $2 signs. There we go. So and then so that means the tangents to omega Y and C and AB concur. Did we even use the fact that it's isosceles? I'll say concur at point I, or no, they concur at a different point. So we don't even need really any of this. Let's see. I'm going to delete everything else that I added. Yeah, we really needed very little. So we have this. Let me draw it in. Oops. I don't even think we need point J. I don't even know what we need here now. So what? Oh. All right. So hold on just a sec. So those two meet on AB. I'm going to draw that point way down there, F. All right. And once we know that, then we want to show angle FYH is equal to angle YDH, but FYH is equal to FYX. Let's see. Yeah, we want to show FY is tangent to YDH. So radial projection. Well, let me see. So we have angle FYH is equal to angle FYX, which is equal to angle YEX. So we want to show YEX is equal to YDH, but that's equivalent to the problem. Now I'm confused. Right, so didn't you say that this finished off the problem? I forget how. Oh, we want to show Fy squared is Fh times Fd. Oh, it's power of a point. Okay. So we have Fy squared is equal to Fc squared is equal to Fh times Fm. So all right. So that means that Fy is tangent to the circumcircle of y, or this should be times Fd. So that means that Fy is tangent to the circle YHD. Okay. And that means that those two circles are tangent. And that solves the problem. So I'll just add the step in the beginning that, what is it? HDC. Oh yeah, we need that HDC is tangent to the, yeah. So I'm gonna write that out. I deleted it earlier, but so angle DHC is 90. That means that the center of DHC lies on OC, and that means that DHC is tangent to ABC. All right. So all right. And then that means that YHD, the circle YHD is tangent to ABC. But where did we use that ABC was isosceles? That's kind of my question. So
ABC isosceles is not needed, I guess.
really? We don't even need that.
You can try proving the figure.
Interesting. All right. I'm going to move on to the next problem just because we've spent a while on this, but that was pretty interesting. All right, so here's the next problem. So